This is the second installment of a series of lectures on special relativity. This particular one is a little more mathematical on the calculus side, and it is just merely meant to be a mathematical introduction to metric tensors. For those who have not seen these before, this will give you the basics behind what they're all about and how one derives them. We will use this type of description in a later video when we talk about forum momenta, etc. This relatively short lecture is going to be divided into three parts. The first part is going to be on manifolds in R3, and then I'm going to distinguish between two kinds of metric tensors. One which you derive using something called an intrinsic approach, and another called the extrinsic approach. They are basically equivalent, but they have a dimensionality difference in them, and I'll show that one is slightly preferred to the other in the subject of special relativity. First, what is a metric tensor at all? This is going to be something called an intrinsic approach, and I'll maybe say what that means later. But in calculus, if you're trying to describe, let's say, a manifold here is simply going to be a surface in R3. The best way to describe it is parametrically. I say the more general ones. So if you have surfaces which have all sorts of ups and downs and valleys and holes, etc., such as a torus or whatever, you want to describe these things parametrically. So for a two-dimensional surface in a three-dimensional space, you can the position vector on the surface at coordinate q, which is only two-dimensional coordinate, can be given by a three vector as listed here. So R of q is a point on the surface or manifold M. Some common manifolds that are described this way, the first one are graphs. So if you say, I tell you the x and y coordinates, then I can tell you the z coordinate by some function f of x and y. But that's a vector, and the set of all points for all the x, y in the domain gives you the surface. The unit sphere can be described by coordinates that are basically longitudinal coordinates and latitudinal coordinates. And if you've taken a class in this, you would have seen this at some point. You can also have the coordinate for a cylinder. In this case, a cylinder of radius a, where you can see the y squared plus z squared is equal to a squared. When you have a surface that is parameterized in this way, you can describe curves that are on that surface in very simple ways. And so suppose I have this parameterization R of q, and I'm going to pick a constant pair C1, C2. If I fix the constant, the Q2 value to be this constant C2, then there's only one variable that's changing in this vector. And as you vary this Q1, what that does is it traces out a curve C1 on the surface. So we'll distinguish that particular curve for that particular C2 value to be R1 of Q1. Likewise, if you fix the Q1 coordinate and let Q2 vary, you get a different curve. Now, these two parameterizations of these curves, they necessarily have to intersect when Q1 is C1 and Q2 is C2. And what that means is that the pair C1, C2 will uniquely determine that point of intersection. And in that manner, C1, C2 pairs describe the coordinate systems or the curvilinear coordinates on the surface. So if I get any pair of C1, C2, that will uniquely define a point of intersection on the surface. And as in standard multivariate calculus, you can easily find out some things about the surface if you take the partial derivative of the r vector in the qi's. You get tangent vectors to the surface, two of them. You can vary q1, leave q2 fixed. You can vary q2, leave q1 fixed. So you get two tangent vectors. And if you take those two tangent vectors and you cross product them, then you get a normal vector to the surface. That's more or less review here. So if you take now let's say an arbitrary curve C on the manifold, and it's got a parameterization of in the following manner. What you do is you let the q's vary in T, and then out of that pair of q's you get a vector r, which is in R3, and that's a curve. I can take the derivative of that curve parameterized in T. So I take the derivative, or the dot is the dot derivative, or the derivative in time. And if I take that derivative and I use the chain rule, I get the following expression, where in this chain rule these first terms are actually vectors. So this particular one that I've just outlined is actually this vector below here. And it's multiplying dq1 dt. So I get this vector with partials in q1s times q1 dot plus a vector in derivatives in q2 times q2 dot. Why do you do this? Because if you want to find the length of any curve and you have a parameterization, it's very easy to do it. What you do is you take the magnitude of this dr dt vector and you integrate it in time. That's standard multivariate calculus stuff. So the length of the curve from one time A to another time B is you take r dot, you find its magnitude, Euclidean magnitude in this case, which is given by, you take, the way to do it is to take the dot product of r dot with itself, and then take the square root, and that's exactly what this norm here is. Well, we have an expression up here, albeit a little bit complicated. So we have this expression here, this first one. Say I take this. No, I can't do that. Well, so this first stuff on this right-hand side here. So that, I'm going to do that dot product with itself. So that's down here now. So r dot magnitude squared is r dot inner product r dot. So that would be this expression on the right. There's the inner product of a sum, comma, another sum. And to do this, you look at it and, well, I'm going to have a whole variety of different terms. I'm going to have inner products of, let's say, this first term with this first term, this first term with the second term with the first term, and so forth. And if I expand this whole thing and group things together, I'll have things that multiply q1 dot squared. I'll have things that multiply the cross terms, which will be q1 dot times q2 dot, for example. And so you'll have two of those. And then you'll have q2 dot squared terms as well. And the things I've highlighted here in red, these things in red are the coefficients of each of these qi dots terms. If you stare at this thing long enough and you know a little bit of linear algebra, you would say, well, you know what? I can write that in a matrix form. And the matrix form is the following. Each of those inner products, the inner product, so you take the inner product of pairs of these vectors. These are tangent vectors. And I do a derivative in RQ, in RQ mu and RQ nu. And there's going to be 4 possible combinations of these inner products. They make a 2x2 matrix. And so we'll give the name of each one of those coefficients a name, and in this case it's G sub mu nu. And if you define that 2 by 2 matrix that way, then R dot inner product is the vector Q dot times the matrix G times Q dot. And then you can write the length of the curve as the square root of this last expression. So to find the length of a curve in this manner, you take the thing, this matrix G, which is called the metric tensor. You perform this operation, take the square roots, dt, and that gives you the length of the curve. In tensor notation, what one would do is you would write this expression down here below in the next term, the next expression. These are the elements, the mu nu elements of the matrix G times the Q mu dot and Q nu dot. And this is an implied double sum in the coefficients mu and nu. So you sum over mu equal to 1, 2 and mu equal to 1, 2. And as a result, you can get a differential arc length element in terms of this matrix G, or the metric tensor. So really what it is it's just if I tell you what the surface is, that basically means stipulate R, then I can compute all of the elements of G, and that's all that I need to figure out the length of curves on anywhere on this surface. And that's what's called the intrinsic approach. Here's an example. This first term here is the parameterization of the unit sphere. Phi is the latitude angle from 0 to 180 degrees, and then the longitude angle is 0 to 360 degrees. And what you do is, if you have the parameterization of the surface, you take the partials in each of the two independent variables, and you get two different tangent vectors. It's the different products. You take all these tangent vector dot product combinations, and they will form this matrix. So for example, this upper left part of this metric tensor is just t sub theta dot t sub theta. And that turns out to be sine squared when you look at these two things. So if I take this and I do the inner product of itself, and I use a trig identity of sine squared theta plus cos squared theta is 1, I get this sine squared phi. Likewise, cross terms are 0, and then the other diagonal term is 1. So here's the metric tensor associated with the unit sphere. Once I have that metric tensor, any surface on that sphere can be computed if all I know is what d theta dt and d phi dt are. And one little example here is, well, what if I have a fixed latitude, and I take the length of a fixed latitude curve, you get a formula for that fixed latitude length. The extrinsic approach is arguably a little bit more general, and what it depends on is only knowing basis vectors and inner products of the basis vectors. What do I mean by that? Well, we're going to describe the surface a little bit differently. I'm going to do it really kind of a straight up approach. I'm going to say, let's suppose I have a basis vectors for Rn. And I've got a point that's on this surface. This is a higher dimensional surface. And it has a coordinate that's just straight up x1 through xn. That's, let's say, Cartesian coordinates. So the point is given by these coordinates times the basis vectors and summed. So here's the tensor notation implying that sum. And now what I'm going to do is I'm going to say, let's change these coordinates. Suppose I have formulas for these xi's, x1 of t, x2 of t, and if I have those formulas and that this R is on the surface for those given formulas, I can very quickly determine R dot again. It's just that now I have a sum of slightly more things. Now, R dot, it's easier to look at, but when I have to do the R dot squared, I have many more terms and many more possible combinations of the inner products. So I'll have the E1 term that will be doing an inner product with the E1 term here, E2 term all the way up to the En. Then I'll have an E2 term here, inner product with the E1 through En, etc. I can expand this out, and then I get the following. Well, it's actually kind of simple. It's the R dot squared. That expansion is given by another matrix, slightly different matrix, the extrinsic version, G, which all these G's are the inner products of the basis vectors, the different permutations. So you can have the 1,1 term of this matrix, you have the 1,2 term of this matrix, and you form all those inner products, and that gives you this matrix. It's going to be necessarily symmetric, and that would give me a formula for the length using this metric tensor. The connection between the extrinsic and intrinsic approaches would be as seen by this formula here. Basically, if you have a parameterization in the Q's, and the Q's depend on T's, that'll translate into, if this is like 2-dimensional, then this will be a 3-dimensional vector. In a really simple example of the extrinsic approach is if you let any you take any basis that's mutually orthonormal in the Euclidean space Rn, and you take all of these inner products of these basis vectors and look at them. Well, I can take all different kinds of combinations. They'll either be ones or zeros. They'll be ones if they're the same vector inner product with itself because they're normalized, or they'll be zero because they're different basis vectors which are orthogonal. So if you work that out, it turns out that the metric tensor in the extrinsic approach is just the identity matrix. In summary, we have here for the extrinsic approach, which is what you'll need for Minkowski Dynamics and Special Relativity, is that we're going to describe curves in space-time as these 4-dimensional vectors parameterized in some parameter t, and the lengths can be found using the metric tensor, and the metric tensor you find by dot producting all of the basis vectors to form a big matrix. And if you have that, then you take that matrix, and here's the formula here, which gives you the length of the curve. Now on this slide here, this is a little different. So I've got the length of that curve, but I've added something else in here. It's that the notion of something called a geodesic. So if you think of all of the possible curves that can be on the surface, there are some curves that are wiggly and therefore longer, or you can have some curves which are just the right curvature to make the shortest length along the surface. The surface can be mountainous or not, or flat or spherical or whatever. But what determines the shape of the curve that is shortest between 2 points is a subject of optimization theory. But basically the problem goes like this. If I tell you a Q for parameterizing the surface, then I should be able to find the L for that Q, given I know the metric tensor. So the question then becomes, of all the possible Q's, which one minimizes this length? The answer to that question is called a geodesic. A geodesic is the curve of shortest length from one point to another on the surface for the given metric tensor. This is not really needed in special relativity, but I mentioned it here as I guess as a bit of a teaser for general relativity, because one needs to talk about the geodesics in general relativity, which has very wiggly space-time. And if you do a lot of work, you can figure out what the equations are for the geodesic curves in force space in general relativity, and they're very messy, and we will not be doing that here, but it fits in with this discussion with special relativity. Just as the last thing here, I tacitly didn't talk about basis vectors that change with the curve, but basis vectors can actually change as you move on a surface. One example of this is if you're moving on a sphere and you think, okay, I want to have a right-handed coordinate system on a sphere that changes as I'm moving on the sphere, then these basis vectors themselves have to be parameterized. And here I've got a basis vector 1, for example. If I tell you what q, the coordinates q of t are, I can then tell you what this time-dependent E1 is. What's relevant in that, if you're using that, so here's this example of this is given in spherical coordinates. Here are this is a right-handed coordinate system for spherical coordinates for being on a sphere, and this is given in typical calculus books. If I have to differentiate this R of t now, I'm going to have a derivative in the x1 formula, x1 term here, but I also have a derivative of these vectors in time. So there's going to be a whole bunch more terms when I take the derivative of this, and a whole bunch more terms when I take the dot product of r with itself, r dot with itself. So that gets to be very complicated, but it's necessary when you talk about things like acceleration in special relativity. And that is the end of this lecture, and the next one I will see you shortly.